So how can we perform an Eclipse attack where we delay the propagation of blocks to a particular victim? So we know that the block delivery time to extend the block delivery time beyond 20 minutes, what we require for the victim is that he must not receive a block header. If he receives a block header, he will disconnect from the adversary and request the block contents from another peer. So we kind of must find a way to avoid that the victim receives a new block header when he is waiting for the adversary to send a block. The second requirement is we must make sure that the victim does not receive a version message. That is because in the version message, we will discuss in a bit, you exchange which block height you're currently at, and this might tip off the victim to know that it's actually being eclipsed. So what about the block header first? So there's a header first synchronization going on in the Bitcoin client, meaning before you sync the entire blockchain, you first sync the header and then later the transaction. So it's called the header first blockchain. Right, so here for the block B+2, you receive first the header, and then later on you request the block content. Now, what about the must not receive a version message? So this is a simplified example of a message exchange between two Bitcoin clients that initiate a connection to each other. So A will basically say, hi, I'm at block 10, and B will say, hi, I have block 15. And then A will realize, oh, I'm 5 blocks late or behind. Can you please send me the headers? And this is something we want to avoid. We certainly don't want the victim to know that it's behind, and we don't want it to receive the headers from another peer. So this is something that we have to kind of make sure it doesn't happen. So to do that, we can occupy all open connection slots of the victim. If we do occupy everything where people can connect to the victim, then there are no new connections and there's no version message exchange to the victim either, which means the victim won't be aware that it's actually behind. So the second requirement for an adversary to delay the delivery of blocks to a victim is that it must be the first relay of all blocks. We know that at 800 connections overall, we have about a 90% probability of being first when propagating a block hash or block header, for example. So we have this one, and we have to perform this connection depletion where we connect to all the peers of the victim. Now let's go through an example step by step. So we have the adversary and the victim, and we do have here a time axis to show the different steps. Now at the first time instance T0, we find like somebody finds a block B. This is like some miner in the network, he finds a block. Now the adversary is currently will be synced up to the header chain. So this is because we have this header first synchronization. He will sync up to the header, and then he will receive the block content. The victim does the same. There's currently no attack ongoing. Now let's assume there's a new block being found by another miner. What happens next is that the adversary will start to attack. So the adversary, we assume that here the adversary learns about B+1, the header as well as the block content, and the victim doesn't, except that the adversary will advertise the header B+1 or the hash of the header B+1 to the victim. Now the victim will request from the adversary, can you please send me the header content, and to later receive the block content, but the adversary will not respond. So this is actually triggering a 20-minute timeout on the adversary side. Right. Now this means that the victim is currently eclipsed, and it will be eclipsed for at least 20 minutes if during those 20 minutes there's no other peer connecting to the victim. Now on average, it takes about 10 minutes to find a block in Bitcoin. So we can assume that the block B+2 is found within 20 minutes here in this example. And the adversary will again attack here. He will advertise the hash of block B+2 to the victim. And this will initiate another timeout that you can see here. Right? So that's actually an independent timeout. It means those two timeouts here are not the same for block B+1 and the block B+2. So these are two independent timeouts, and they can run out or expire independently. Now the victim is still eclipsed, and now actually it's going to be eclipsed for probably more than 30, almost 40 minutes. And what the adversary can do, if this timeout here expires, the victim is not doing anything. That's what we've seen earlier. So if the timeout expires and the victim has not received anything, any header from other nodes, then it will not request the contents from any other peer. And that's why the adversary can very gently re-advertise the hash at this point in time and recreate a timeout for this particular block B+1. So let's assume now there's a block B+3 that's found, and here the adversary chooses to not attack. So we had here the symbol for attacking, and now we assume that the adversary will not attack. So what will happen is that the victim will learn about the header B+3. So the header chain will actually be synced up quite quickly for the victim again. But he can still not verify the transaction content, so the new transactions that he's receiving, because he's behind for the block content of B+1 and B+2. So only when this timeout here expires, the victim will learn about block B+2. And at this timeout here, the victim will then learn about B+1. And only when it learns about B+1, it can actually connect the blockchain by going from B to B+1 to B+2 to B+3. And that's the entire attack. So in order to, this is the theory, right? In order to experimentally validate, so we can assume here a certain probability for being first in advertising a block, which is about maybe 80 to 90%. So here we chose this number. So if we plot the number of consecutive blocks that we can deny to a victim, you can see here that with about 40% probability, we should be able to deny or to eclipse the victim for 5 consecutive blocks, which is on average 50 minutes. And experimentally, we measured this and we tried this, and this is what we find. So it's actually more or less expected. It's quite close to reality.